Assalamualaikum. My name is Muhammad Hanif Ahmad bin Subahi. My meeting number is DE190107, and we from Group 6 will do our presentation for our PBL activity 2. So first, introduction. Analog to digital converter (ADC) are an important component when it's come to dealing with digital system communicating with real-time signal. To transmit this analog data over digital signal, we need analog to digital conversion. Analog data is a continuous stream of data in the wave form where digital data is discrete. To convert analog wave into the digital data, we use postcode modulation, that is PCM. This PCM is a digital scheme for transmitting analog data. It converts an analog signal into digital form. Using PCM, it is possible to digitize all forms of analog data, including full motion video, voice, music, telemetry, and there are three processes involved in doing the analog to digital conversion, that is sampling, quantization, and encoding. That's all from me, and I will pass to the next presenter. Thank you.
Hello, my name is Muhammad Arifin Azman. My metric number is CE190131. I'm going to explain about brainstorming process for this project. And let's go to the part of filler table. As for the filler table here, there's four main components: facts, idea, learning outcome, and action here. And for the first part is fact, we're given that figure 1, which is block diagram to encode and decode an analog modulating signal using pulse code modulation technique in digital transmission. For the ideas, find information about PCM technique to analyze the complex problem of analog to digital conversion and digital signal transmission. As the matter of learning outcome, sampling rate is restricted by the Nyquist citation. Sampling rate of Fs equal to 2 FM is called the minimum Nyquist rate. And for the last action, come up with solution to make sure the resultant recovered signal is same or similar to modulating signals, and find the result by simulation help to analyze the data. And with that, we go to flowchart. Flowchart is a brief on the purpose of flowchart is to outline the process main component while providing a larger picture of the brainstorming process. So this is a draft to ideas how to we manage this project with the given that's different scenarios, and to analyze and discuss the resultant recovered modulation signal. There's for part A, B, C, and D scenarios. Scenarios is being done with the help of software simulation and analyze the data to make sure there's the need to suggest to make sure the resultant recovered signal is same or similar to modulating signal. With that, if the best approach is approved, it is okay. However, if not, we will repeat the same to find the better outcome for the best to conclude the result of the rest of the studies. I think that's all from me.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Fikri Hadi Besbawi. My matrix number is AE10041. And now I will continue the presentation for the simulation in MATLAB Simulink. Okay, we need to build this circuit into this MATLAB, and this is for the equation, and we have 5 scenario. Now we look for the circuit. Okay, this is only for the 4-bit encoder. We have 2. The other one is 8-bit encoded. So I will show you the 8-bit encoder after this. Right now I will show for the scenario 1 only. Okay, the value that we need to change is only for the period. The value for period is 1 over 200. That's all. Why I get like that? Because the fs for the scenario is 2 fm, and then the value for the pulse width 50, phase delay is 0, and the amplitude is 1. For the modulating signal the amplitude is 5. We got from here, you can see if 5 seen, that's why I get if 5. And for the frequency 100, and that's all. And then we run. Right now we will see for the signal for the sample and hold 1, encoder, decoder, and sample and hold 2, and also analog filter. And we will also look for the oscilloscope. Okay, the first one is for the SNH1, this for the encoder 1, this for the decoder 1, and this is for the SNH2, and this is for the filter, and the last one is for the oscilloscope. Okay, and the most important, the graph for the 4-bit encoded present display. This is the result. Okay. Okay. After that, we can proceed for the other scenario. For the 4-bit encoded, for the scenario 1, we will only change the period. The period was bigger, the fs bigger from 2 times fm, and the scenario 5, the fs is lower than 2 fm. That's all. We need to change only the period. I will show you where we want to change at here. And for the scenario 3, we change for 400 because it's 1 as to change is bigger than 2 fm. And for the scenario 5, we will choose 100 because it was lower than 2 fm. That's all. Okay, right now we continue for the 8-bit encoded. The thing that we just need to change is this one, and the value is also same for the second scenario. For the period is 200, for the scenario 4 is 400, and we don't have scenario 5. We only have 8-bit encoded for scenario 2 and scenario 4. That's all. It's just same method. We just need to change it here, and we run. And the only thing that different, the result different is for the display. You can see we have 8 display for the 8-bit encoded. Okay, that's all. And for the graph, I think it's only same. It's just same. It's only for the 8-bit encoded. That's all. Okay, for the part D, we need to set in the public remain, and it asks what will happen to the recover message empty if amplitude of empty is changed to 50 and 0.5 volts. Okay, where we want to change the value is at here at the modulating signal. This amplitude we will change to 15, and then we just need to change to 0.5. Okay, we will see for the amplitude 0.5 result. And we run. Okay, let's see here. We can see the graph change. For the encoder 1 also change. For the decoder 1, it's also change. It's same. The filter also change, and the oscilloscope also change. The last one is 8-bit encoded present display. You can see the result here. Okay, I think that's all for me. Thank you. Okay, Bismillahirrahmanirrahim. Right now I will continue for the result. For the first thing we need to prepare is for the number of quantization, voltage range, resolution, and maximum quantization error. As you can see, this is the value for both 4 bits and 8 bits. You can see here. And now we proceed for the part A. FF is equal to 2FM. Okay, FS we got for 200. You know, I explained from the simulation. And this is the sampling signal on sample and hold 1 and filter. The blue waveform shows the sampling signal after had been through the sample and hold process, while the yellow waveform shows the sampling signal before the filter process. We can see that the amplitude of sampling signal after the transmission is lower than before the transmission. Okay, this is for the encoded signal, this is for 4 bits, this is for 8 bits. You can see the difference from both bits. Encoded signal in 8-bit is much higher than signal of 4-bit. You can see that. That's why the encoded signal in 8-bit is higher than signal of 4 bits. Okay, for the PCM signal, the only difference for this graph is only the number of signal. As you can see, for the 4-bit, it have only 4 bits, and for the 8 bits, it have 8 signal, 8 graph, and it have 4 graph. Okay, this is for the analog signal before and after transmission. The blue waveform indicates modulated signal, while yellow waveform indicates for recovered signal. So after transmission, we got the smooth sinusoidal wave, but the amplitude is lower than the original signal, which is about 3.093 volts for 4 bits, and for the 8 bit is 3.389 volts. Okay, we proceed for the part B. Fs is higher than 2 Fm. So the Fs divided for Fs is 400. This is the sampling signal on sample and hold one and filter. The blue waveform shows the sampling signal after having through the sampling process, while the yellow shows the sampling signal before the filter process. As you can see, the amplitude of sampling signal after transmission is lower than before the transmission. Okay, this is for the encoded signal for 4 bits and this for 8 bits. The encoded signal in 8 bits also much higher than signal of 4 bits. And for the PCM signal, you can see the difference from the part A, but the number of graph is same. For the 4 bit have 4, for the 8 bits has 8. This is the 4 bit and 8 bits pulse code modulation signal before the transmission to the receiver. This is the graph for the analog signal before and after transmission. The blue waveform indicates modulated signal, while yellow waveform indicates of recovered signal. After the transmission, we got the small sinusoidal wave, but the amplitude is lower than the original signal, which is about 3.108 volts for 4 bits, and for the 8 bit is 3.442 volts. That's all from me. I will pass to my other members to continue the explanation. Thank you.
Hi, Assalamualaikum. My name is Muhammad Zikri bin Hamid, electric number KE 10007. The next we will see for the part C, which are the result for Fs is less than 2 Fm. So in our cases, we use 100 Hz of frequency. So we can see the result in the scenario 5, which are for the 4-bit system. The first is the sampling signal. So here the result of the sampling signal. So from the graph, we can see that the amplitude of the sampling signal after the modulating and the transmission signal is lower than the sampling signal before those process. It is mainly due to the losses during the transmission and modulating process. The next is for the encoded and the PCM signal. So here the result. And lastly is for analog signal before and after the transmissions. So from this graph, we observe that we do not get the smooth sinusoidal wave. This is due to we have the ripple on the peak of the signal for both modulating signal and also the recovery signals. And also the amplitude is lower than the original signal, which is about 2.949 volts. Which for the original signal is 5 volts, so it is much lower than the original signal. And next we will see for the part D. So for the part D is same with the part B scenario, but with different amplitude. So for the part D is 400 Hz of sampling frequency. So for the first one, we will see for 15 volts of value. So for the 4 bits, we got the quantization error is 1 volt, while for 8 bits, we got 0.0588 volts. So here are the results for the our 15 volts amplitude value. So what we want to see is the output signal. So after the transmission, we got the sinusoidal wave, but the amplitude is lower than the original signals. So the original signal is 15 volts, but for 4 bits we got 9.324 volts, and for 8 bits we got 10.32 volts. So it is much lower than the original signal that we want. So second, we will see for 0.5 volts. So for this amplitude, the quantization error for the 4 bits, we got 0.03334 volts, and for the 8 bit, we got 0.002 volts. And here are the result for 0.5 volt of amplitude. And here are the analog signal before and after the transmission. So after the transmission, we got the smooth sinusoidal wave, but the value is also lower than the original signal, which for 4 bit we got 0.3108 volts, and for the 8 bit we got 0.3442 volts. So this value also lower than the original signal that we want, but the difference is lesser than we use the 15 volts of amplitude. So the suggestion to make sure the resultant recovery signal and prime T is similar to the return signal, and T is which suggests to use the 8-bit of encoded PCM data to transmit to the receiver. So this due to the 8-bit data will minimize the maximum quantization error of the data. So we can say that the 8-bit system is more accurate than the 4-bit system. And next, in order to increasing the peak of the maximum value of the signal, we add the gain block in the simulation of MATLAB Simulink. As we can see from the result previously, the value after the modulation and the transmission process will be decreased. So by adding this gain block diagram, we can increase the amplitude of the signal to be similar to the modulating signal of the original signal. So here are the result after and before and after we adding the gain in the MATLAB Simulink. So we can see here that after adding the gain, we got the similar value of the amplitude to the modulating signal. So that's all for result. Thank you.
Hello and Assalamualaikum. I am Muhammad Nur Fazari bin Adnan and my matrix number is AE19060. So, the conclusion is in this project, our group are required to encode and decode an analog modulating signal using passcode modulation technique in digital transmission with different scenarios to be analyzed and discuss about the resultant recovered modulating signal. So based on the result obtained from manual calculation and simulation for each problem from part A until D, we need different type of approach, and according to the results, part B produced a superior output signal than part A. The reason for this is that the sampling rate of part B is greater than the sampling rate of part A, which is the minimum sampling rate for the signal. And for part C, sampling rate is less than 2 frequency max, and some of the highest frequency components cannot be properly digitized. Part D shows that an amplitude of 0.5 volt result in a relatively low quantization error when compared to 15 volt. In terms of amplitude, the 0.5 volt signal produces a superior output signal. So this project helped in increasing our knowledge in using the simulation apps to solve problems with many scenarios. Uh, and it also help increase our skill in using the simulation app to solve the problem. So that's all for conclusion. So that's all for me. Thank you.